This is a pre-built version of the application. So if we run the server and the two clients, so this will be the server and this the first client and this one the second one. So Alice picks those two prime numbers and calculates n and phi of n, and she picks this public exponent from this set where the inverse of E exists, meaning the GCD of E and phi of n is equal to 1. So she ends up with this public key made up of n and E and this private key. And Bob picks those two prime numbers and calculates n and phi of n, and he picks this public exponent from this set where the inverse of E exists, meaning the GCD of E and phi of n is equal to 1. So he ends up with this public key and this private key. So now both Alice and Bob can send and receive signed messages from each other. So let's say Alice wants to send this message to Bob. So she starts by mapping the characters to ASCII and obtaining this ASCII message, and then she needs to enter her private key to sign the message with. So this key. So let's first try with a made-up key and see what happens. So she ends up with this signature S and this signed message made up of the message and the signature. So X and S, and she sends that to Bob. And he receives that signed message and uses Alice's public key to determine if the calculated message X prime is the same as the message X. So he calculates X prime and compares it to X, and it is different. So this is different from this. So he concludes that the message was not signed with Alice's private key. So let's try now to send the same message, but sign it with Alice's private key. So 191. So now Bob receives that signed message and uses Alice's public key to determine if the calculated message x prime is the same as the message x. So this turns out to be x prime, and it is actually the same as x. So the message was signed with Alice's private key. Now here we did not encrypt the message, so we do not have any confidentiality since Eve can see the message. And since only Alice and Bob have access to their private keys, so using those keys to sign messages authenticates those messages as having been signed by Alice or Bob. And for Eve to change the message, she needs to have access to Alice's private key and Bob's private key. Otherwise, if she did change x, then x and x prime would not match. So we do have message integrity since the message was not changed in transit. Now before proceeding with the code, let's do a quick introduction. So this was the name of the original RSA paper, a method for obtaining digital signatures and public key crypto systems. So digital signatures was part of RSA from the start. So our goal is to build a prime factorization based digital signatures and public key crypto system. So we start by multiplying two large prime numbers, P and Q, and obtaining the result N. Now it is not computationally feasible to figure out P and Q from N. So in our crypto system, N has to be known and P and Q unknowns. And we want to set up the system in such a way that there exists a private key D that is the inverse of the public key E, and where it is very hard to figure out D from E in mode something. Now if the something is known, then we can use the extended Euclidean algorithm to figure out the inverse. And this was the extended Euclidean algorithm, and it is used to compute the inverse modulo of an integer. So for example, to compute the inverse of 7 in mode 19, we end up with 11 as the inverse. So the something has to be the unknown in our crypto system, meaning it has to be based on P and Q. But we also know that for two prime numbers, P and Q, the Euler phi function, phi of n is equal to P minus 1 times Q minus 1. So this was Euler phi function. So phi of m denotes the number of integers in Zm that are relatively prime to m, where Zm is equal to the set of integers from 0 to m minus 1, and two numbers are relatively prime if their GCD is equal to 1. For example, if m is equal to 15, then Z of 15 is this set from 0 to 14. So we take the GCD of 0 and 15 and 1 and 15 and 2 and 15, etc., and we end up with those GCDs equaling to 1. So we have 8 of them. So phi of 15 is equal to 8. Now if m is very large, it is not computationally feasible to count GCDs. So we use those formulas for m and phi of m. So m is equal to p1 to the power of e1 times p2 to the power of e2 times etc. pn to the power of en, and this is phi of m, where pi is a distinct prime number and ei is a positive integer. For example, if m is 200, then we end up with 5 to the power of 2 times 2 to the power of 3. So p1 is 5, p2 is 2, and e1 is 2, and e2 is 3. So we end up with phi of 200 is equal to 80. Now if p is prime, then phi of p is equal to p to the power of 1 minus p to the power of 0, so it is equal to p minus 1. And the GCD of p and q is equal to 1 means that the phi of p times q is equal to phi of p times phi of q. And if n is equal to p times q and p and q are primes, then phi of n is equal to phi of p times phi of q. So phi of n is equal to p minus 1 times q minus 1 from here. So if m is equal to 15, then we end up with phi of 15 is equal to 8. So same what we obtained by counting GCDs. And we know that for very large numbers it is not computationally feasible to obtain all GCDs and count the relatively prime numbers. So the idea is to use phi of n as something and set up the system such that d is the inverse of e in mode phi of n, and e is in the set of 1 to phi of n minus 1. So we end up with those 5 steps. So the public key will be n and e, and the private key will be d. And we encrypt by using the public key, and we decrypt by using the private key. And for digital signature, it is reverse. We sign using the private key, and we verify using the public key. So we use the private key d to sign x in Zn from 0 to n minus 1, and we obtain s, the signature, is congruent to x to the power of d in mode n. And we verify the signature s in Zn from 0 to n minus 1 by using the public key n and e, and we obtain x prime is congruent to s to the power of e in mode n. And if x prime is congruent to x in mode n, then we have a valid signature, and if x prime is not congruent to x in mode n, then we have an invalid signature. I will start by creating a new project. And here we will have two packages, one for the server and another one for the client. And on the server side we will have two classes, a server class with a main method and a server thread class. Which will extend from thread. And on the client side we will have three classes, a client class with a main method and a client thread class, which will extend from thread, and this class will contain the RSA digital signature logic, and the server thread will have those three instance variables: a server and a buffered reader and a print writer. And the constructor takes in a socket and a server, and it uses the socket to initialize the buffered reader and the print writer. And we have this method that forwards messages, and this server will accept connections on this port, and it will have a set of server threads for the different clients that this server is interacting with. So while this server is running, we accept connections from clients and instantiate server threads for those connections, and add those server threads to this set, and start the server thread. And here Eve indicates that she can see all communications, and this is just a get method for the server threads, and this method does message forwarding from Alice to Bob, or the other way around. And here when we call start, we end up triggering a call to this run method when the operating system decides to do so. So actually I forgot to pick up this package from here. So we'll go to properties and Java build path, so if the JSON message coming in through the server contains the public key, then I indicate what that public key is, so N and E, and indicate that we need the private key D, and to obtain it we need to do prime factorization of n into p and q. So if we obtain p and q, then we can obtain phi of n, and if we obtain phi of n, then we can obtain the private key d. So this should do it on the server side. And the client will have those instance variables, and get and set methods for them. So we will keep track of the username for this client and for the other client that this user is interacting with, and n for this client and for the other client, and the public exponent for this client and for the other client, and the private key for this client. Now going here, we will have those two methods for calculating d, the private key, and phi, so p minus 1 and q minus 1. And this method checks if a number is prime, and this one checks if two numbers are relatively prime, and this one turns character to ASCII, and this one ASCII to character. And this method handles picking up P and Q from the user and the username. And here we make use of the is prime method, and we set n to be p times q, and we calculate and set phi, and we prompt the user for the public exponent, and we make use of the is relatively prime method, and we end up calling this method from here. And here we calculate and set d, the private key, and send the public key to the other user. And this method handles the receiving of public keys, so here we are picking up E and N, the public key, and the name from the JSON message. And this method handles the signing of a message, and this one handles the sending of signed messages. So here we prompt the user to enter the key to sign the message with, and we call the sign message method, and we send the signed message. So this is the message, and this is the signature. And this method validates signature on the signed message. So we use the public key of the other client to determine if the calculated message x prime is the same as the message x. And here we calculate x prime and compare it to x. And this method handles the receiving of messages, so it makes use of this method here, and we indicate if the message was signed with the other party private key or it was not. So this should do it for this class. And here we will have those two instance variables, and we will initialize them in the constructor. Which takes in a socket and a client, and uses a socket to initialize the buffered reader instance. And the server will be listening on this port, and we instantiate and start a client thread, which will end up triggering a call to this run method when the operating system decides to do so. So if the incoming JSON message contains a public key, then we call the handle receive public key. And if it contains the signed message, then we call the handle receive message. And here we handle key generation, and the user entering and sending signed messages. And finally, let's go ahead and test run the application. And this will be the server, and this is the first client, and this the second one. So Alice supplies those two prime numbers, and this public exponent. And ends up with this public key and this private key. And Bob supplies those two prime numbers, and this public exponent. And he ends up with this public key and this private key. And let's have Alice send this message and sign it with a made-up key. So she ends up sending this signed message to Bob, and he receives it and determines that that message was not signed with Alice's private key. So let's go ahead and pick up her private key. And let's try to send the same message again. And now sign it with her private key. So now Bob receives that message and determines that it was signed with Alice's private key. And let's have Bob try to send this message to Alice and sign it with a made-up key. So Alice determines that the message was not signed with Bob's private key. So let's have him send that message again. But this time we'll pick up his private key and sign the message with it. So now Alice determines that the message was signed with Bob's private key.